So hello, good morning everyone. So I'm Eduarda, and today I'll be presenting our notebook for network and topological analysis in neuroscience with Fernando. So we both work in Amsterdam at the MultiNet lab, and this work was part of my master thesis last year. So just to give you some context, the MultiNet lab, we try to investigate how the brain works through the prism of networks in health and disease. And we have different imaging modalities and also cognitive and demographic data. Oh, there's some I'm sorry for that. My computer was not like that. But for this project, we focused mainly on functional MRI. Sorry. Okay, functional MRI.
It's because you have animation.
So since I know that this might not be your area of studies, just to give you an overview, so fMRI, basically we try to keep track of the activity of the brain. And this is basically based on the Douw signal. So when an area of the brain is activated, you have more influx of blood. And this will lead to an increase in the signal that the machine can keep track of, and we can have this time series of brain activity in the end. So we work mainly with resting state fMRI, which means that the patient or the subject is not involved in any specific task. They are just laying there, mind wandering. And we're looking for the spontaneous brain activity. And once we collect this data, we can extract the time series from these different brain areas, and then use a Pearson's correlation to obtain a correlation matrix. That's where our notebook starts. So we don't really cover the pre-processing part. We focus mainly on the analysis, starting on the connectivity matrix. So, as I mentioned, we try to understand it through the prism of networks, and we can use this connectivity matrix to transform into a graph in which the brain areas will become the nodes, and the link between these areas will become the edges or links. So it's a Pearson's value in this case. And the classical framework that is used in this field is graph theory. So it allows us to use different observables to try to understand how these networks are organized. If there are specific features between different groups, for example, or something that is different than no models. So we can try to understand how these networks are organized and get some insights. So we already obtained some information about the brain using this framework, which has been quite important. So we now have this idea that the brain seems to have this compromise between integration and segregation. So you have some local processing, but you also have some long-range paths. But these are they're high costly for the brain. So the brain cannot keep a lot of long paths. So there's a balance between integration and segregation. And we also know that there are areas in the brain that work as what we call hubs. So they seem to be more important than others. And when we are trying to understand disease, for example, this is really important because we can try to see if this hub is being affected mainly and how this might affect the behavior of the patient or the cognition of the patient. And in the past years, a new framework is emerging and starting to migrate into neuroscience, which is topological data analysis, and which is Fernando's main field of work. And the idea is that we go beyond these dyadic relationships and try to understand this data in a slightly different way. So high order interactions, and also TDA might be more robust against noise, which is a big problem in neuroimaging. So that can be very useful as well. So I'm not sure if the video will play. No,
it won't play because we have not quick.
Okay. So the video won't play, but I can show it afterwards.
Is the video in the folder?
Yeah, I do afterwards. Yeah, but it's no problem. I can leave it afterwards. Yeah. So for this work, our goal was really to facilitate the computation of network and topological analysis to clinical neuroscientists, because like me, I don't come from maths and physics background. So if you try to explain sort of analysis to people that don't have this background, it can be quite tricky. So it's important to have this sort of educational resource in which people can learn how to start and where to begin, basically, to learn about these things in a very digested way, let's say. So we also noticed that there was this sort of gap in the visualizations of high orders in brain data in the literature. So Fernando has been working on that for a few years now. And we developed this high order visualization, which the video was supposed to show, but I'll show it later. And of course, we wanted to be in line with open science, which is a major part of my career, but also in the lab. And for that, we created a A to Z hands-on tutorial in which we guide people from the connectivity matrix to this different sort of set of observable and analysis. And we used open source tools and open access data. So we use Python, Jupyter, Binder, GitHub, and we provide both a computational and a theoretical information. Let me just, the slide is sort of, oh, sorry.
Yeah.
This slide is a bit very, using the
PDF.
You know, you can open the, but not in the presentation mode, please, if it's possible. The slide, let's see. Yeah. Just because it's quite using the formatting. No, I mean, can you share the?
I can share.
No.
The video?
The slides again, sorry.
Oh, the slide.
Yeah, it's just because it's lost some the formatting and it was important. Okay, so I closed it. Yeah.
What did you close?
Yeah.
So no. No.
Okay. It's okay. It's open in this presentation mode. Yeah. No problem. Yes, there should be some links below that you can see if this looks fine. So yeah, so basically we have the computational part on GitHub, which are the notebooks that I will show now, and the theoretical information is on bioRxiv already. So I'm sorry for the formatting, I was not aware. And now I will start with just the bioRxiv. So here we really try to summarize the background behind these observables and give an easy introduction to the topic, to a neuroscientific vocabulary, let's say, as well. And we provide a list of resources, which I'm going to show now.
Yeah.
Sorry. Yeah. Here. So we really try to make it easy for everyone. So of course, this is like by no means a complete overview of the field, but it's really a start point for whoever wants to begin. And we provide computational resources and some Jupyter notebooks and also Python and MATLAB so that people can understand where to start. And also some key readings, at least that for me, and we made a sort of a selection from what we use building this project. But of course, there's much more than we put here. So, and then now for the GitHub, let me just open the link. Let me see if I can open the link.
It's link where?
It's in the presentation.
Oh, so you cannot because it's a commentaries.
Okay, so what?
You cannot access.
I'll open the image, then it should work. So, I can.
Is the image here?
Yeah, I just have to open this first.
Okay. So.
Yeah.
Yeah.
Okay, so I just have to zoom. A bit less, yeah. Good. Okay. The presentation.
Okay. Sorry for the wait.
Yeah. So basically, we have this GitHub page. You can easily access it online. Do you mind if I scroll? No?
Yeah. You have to do.
Yeah. And basically, we show here how you can install everything, how you can use everything in this package in Python, this tutorial is in Python. And mainly what I wanted to show here in this page is that because we are also taking into consideration that some people might not be familiar with Python or programming so much, we also provide the Jupyter notebooks through Binder. So basically you can run them without having to install anything in your computer. And these notebooks, they are divided in two parts. So the first part is, this is the second part.
Go.
Yeah, okay.
Yeah.
Okay, and there's the first part. Okay, yeah, here. So for the first part, we mainly explain how to start with the connectivity matrix. and how to import your data. And then we show some graph theory computations, and mainly using the package called Network X. And then we go to topology and geometry, where we use mainly this package Goody, but we also use Fernando's code. So he developed some codes on the Euler characteristic and curvature and phase transitions. So this is really the beginning of the project. And then on the second part, we have a notebook that is dedicated for the 3D higher order visualizations, as I mentioned, which Fernando will present now.
After all this nice presentation from Eduarda, I just keep 1 minute about the visualizations. So for people working in high order interaction like Giovanni, I think it's a challenge to represent simplicial complexes in 3D. So especially in the brain, and if you work in a team interdisciplinary with clinicians and stuff. So if you tell you what is a simplicity, it's okay here, but within the medical colleagues, like it was hard to visualize. So we developed a mesh generator that we get for, you have a dictionary where you have a list of your simplices and like the sequence that you want to plot, so you can create a 3D mesh for a simplicial complex, and then we project it in a brain atlas. So the code is rather robust. So if you change the brain atlas, if you put in the same format, you could test that for different atlas, so you can really reproduce in 3D. So the first version was made 2 years ago, and then we like did with some real 3D like a brain shape that that's what I illustrate now. So it's nice and exploratory, and also allows us to include metadata. Like we can include the annotation about the area of the brain or whatever you want. So it's makes it more intuitive. Like that was the first version that Eduarda showed a paper of us 2 years ago, but now we kind of develop something more realistic, let's say, for clinicians, and that made a translation between like algebraic topology and medicine, hopefully a bit better. So if anyone wants to try, it works for anything, not only for the brain, but you can, the code is free in Python, so you just need to change the dictionary with the coordinates, and then you would have a list of meshes based on your clicks. We only did here for the vectorial complexes, but we try new things like a PR stuff or other information theoretical metrics that could define simplices, so it will be feasible. But for now, what you have like ready-made to illustrate is on the click complex. Yeah, I think that's all about the visualization. We also did visualization of curvature, which is also on top of this conference. Like there are several curvatures, so you use a simple one, like based on the Euler characteristics, a combinatorial curvature. But then we can also make maybe there is in the notebook. So if you have a curvature distribution in your simplicial complex, you can also represent in 3D, and basically the size of the nodes are proportional to the absolute value of curvature, but you have a color grade if it's negative or positive curvature, and you also need you can also kind of explore if you have metadata about your. And
you can visualize the brain areas when you scroll here. That's something that is quite useful if you're investigating the data as well.
Yeah, if you know like the anatomy, so I'm not the best one, but if you know neuroanatomy, each letter that represents a part of the brain, like the prepineus or thalamus or whatever. So that was kind of made it easy, the bridge. So we hope that. Okay, I think that was it about the visualization. And thanks so much. So we are very interdisciplinary team. This is a photo of our team is led by Douw, the one here. But then there are people on different fields, like mathematics, physics, psychology, neuroscience, medicine. So that's also now multi-network in Amsterdam.
I'm just going to share the video now so we can finish.
I just have to finish it.
Yeah, the last thing that so we made, because then we can make a filtration. So I think everyone here is familiar with a filtration, with section topology, neuroscience, but because we could do the simplicial complex for any level of connectivity, we actually made a filtration. Of course, you cannot show for all simplices. We can do for until like I don't know, we did until 15 like dimensions, but we made a kind of video of filtration up to four. Yeah.
What is the task?
Sorry?
What is the subject doing?
Nothing, it's resting state. Yeah. So that's it. Sorry, sure again. Okay. So this is the video. Yeah.
Yeah, you can see that it gets a lot of simple variation, but
and we are at a low density still, right?
Yeah. But you can represent a high order. If you have a good computer, you can do for higher simplicity. Like the script is robust. Like you just enter the simplicity and the coordinates for the simplices, and then you represent. I think I maybe should mention, I discussed, I think, with Pierre yesterday, that I didn't check for planarity. Like if the coordinates are in the same plane, you mess up a mesh 3D algorithm. So if you have a coordinate that's in the same plane, maybe be careful. But apart from that, it works.
So thank you very much.
Thank you.
Thank you.
Okay, thank you. I don't know if there is any question. I think we have 1 minute to ask them.
Just one question, perhaps.
Everybody's very okay.
Yeah. Can you come here? We cannot hear you there.
That's just very simple question, but can you embed some images in new nice 3D shapes there also?
Yeah, that was the last part because I was not an image guy. But yeah, that's what we did. This 3D shell, we embedded the image. So if you have another shape in 3D, you created this 3D object. Then you can, because this is built upon this plot library. So each of these images are independent objects. So you put a new object, it just superposes. But you have to set up transparency or things like that.
Okay, yeah. And maybe if you have like a MRM brain, can you take out the mesh?
Yeah, we like there is like after the output, you can select which part of the mesh you want to put.
Okay, maybe I'll try.
Please.
Thank you.